Hello everyone. Oh god, my hair's a mess. Hello everyone. Okay, so in this video we are going to be looking at exponential functions, right? So what is an exponential function? Well, an exponential function is in the form a b to the power of x. So it would be something like we have a constant a times something to the power. So the thing about exponential functions is how we know it's an exponential function is my input or my x value is on the index part or like a power, right? So that is how we know it's a exponential function. So we were used to just timesing or squaring or cubing our inputs, but this time where our inputs are going to be powers. So if you look at here, this is what an exponential graph looks like. So these are some key traits of an exponential graph. The first one being it can never cross the x-axis, right? No matter how hard you try, an exponential graph will never cross the x-axis. That's because, right, say for example, this 2 to the power of x here, right? There's nothing I could put 2 to a power of that would make it equal 0, right? Nothing will make 2 to the power of something equal 0. So therefore, it can never cross the x-axis, nor can it make it negative. Another thing is, another key trait about exponential functions is how fast it grows. You can see here, it's like it's all like la 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 la. I'm an exponential function. I don't increase much, and then zoom, and then it shoots up, right? So that's why when people say like oh my god, like things are increasing exponentially, like that just means it's growing very, very fast. So that's the thing with exponential functions. And then finally, the last thing we need to know is, so the graph of function equals a b to the power of x. Remember will pass through the point 0a. So the coefficient of my function is always going to be the y-intercept. So for example, if I have, say, 10 times, so I'm using a dot multiplication here, 10 times 2 to the power of x, my intercept will be 0, 10, right? My y-intercept would be 0, 10, right? If I had 27 times 5 to the x, my y-intercept will be 0, 27. That's because if I put in x is 0, because remember the y-intercept happens at x is 0. So if I do this example up here, x is 0, put it in, I'll have 10 times 2 to the power of 0, which is equal 10 times anything to the power of 0 is 1. 10 times 1, and that answer is 10. Right? So my y-intercept will always be the coefficient of my exponential term. Anyway, graphing exponential functions, it's the exact same. It's the exact same thing we've been doing. You make your 4 columns, you have your inputs in one, your function in the next one, your outputs in the other one, and then your quarters in the last one. You plot them all out, extend it a little bit, bada boom, bada bing. That's all we do. So let's look at this one just for example. It's already done, right? So plot the function f. So x maps to 2 to the power of x with the domain minus 3 to 3, right? That's my domain I'm working with here. Well, there we go. If you have a look here, so when x is minus 3, 2 to the power of minus 3, that will equal to 1/8. So my first coordinate is minus 3 and 1/8. So you notice how I'm dealing with very small numbers here. That's usually the case with exponential functions. You're going to get some very small numbers at first. Again, you have a margin of error in your exam you're working with. So like, don't be too put off or stressed or make a graph so big so you can include like 1/8. You know, like if you kind of put it small enough, you will be fine. So here's all my corresponding points. When x equals minus 2, we have 2 to the power of minus 2, which is 1/4. When x equals minus 1, 2 to the power of minus 1, which is equal to 1/2. 0, 2 to the power of 0, anything to the power of 0 is 1. Again, 1, 2 to the power of 1 is 2. 2 squared is 4. 3, 2 cubed is 8. So 3, 8, 2, 4, 1, 2, 0, 1, minus 1.5, etc., etc. And here it is kind of plotted out, right? So you notice how my y-axis is going up in ones, right? But I just made it really small for an eighth and a quarter and a half, etc., etc. You plot it and you see how it increased muy rápido, very quick. So let's look at an example here together. So, bacterial growth can be modeled using exponential functions. The population of a particular bacterium is modeled by the function px, which equals 100,000 times 2 to the power of x, where x is the time in hours. Graph the population function for the first 4 hours of growth. So, for the first 4 hours, right? So, it'll be 0, 1, 2, 3, 4. The first 4 hours of growth. Now, I already have my table done here, right? So, what I did here was we simplified it down to hundreds of thousands. So, this 1, 2, 4, 8, 6 down to means 100,000, 200,000, 400,000, 800,000, 1,600,000, right? But if you want to actually get the points yourself without having to do all the hard math, exact same thing, calculator, right? So, menu, table, just click 3. Here's my function, put my function in. So, you can put the 100,000, I'm going to put the 100,000 in, just cause 100, 1, 2, 3, times 2 to the power of x, enter power of x, equals, I am starting at 0, I'm ending at 4, going up in ones. And there you go, 100,000, 200,000, 400,000, 800,000, and then 1,600,000 or 1,600,000 or 1.6 million. Right, so let's plot these points out. Right, so we established I'm going up in 100,000 and I'm saying this is population in 100,000. So my first point is 0, 1. There's my first point. Next point, 1, 2, 2, 3. No, sorry, 2, 4, 3, 8, and then 4, 16. There you go. There's my graph. And now it's asked me here, use your graph to estimate the population size after 2.5 hours of growth. Well, I'll go to 2.5. I have my x value. I go up, ding, read it, go across, boom. So that is roughly going to be equal to like 5.7. So starting at the x-axis at x equals 2.5, we move vertically upwards until we hit the graph. That's what we did, and we hit the exponential graph function. We estimate the y coordinate of this to be 5.7. But now, so what's the population size? There's not population size. Is not going to be 5.7. It's going to be 5.700,000, which is 570,000. So let's look at some exam questions. This is from the 2018 Genius, their high-level paper. So a sheet is folded in half a number of times. H of x is equals 2 to the power of x is the number of layers after x folds. Fill in the table to show the number of layers after each of the first 6 folds. So after one fold, so it's modelled with 2 to the power of x. So 2 to the power of 1 is equal to 2. 2 to the power of 2 is equal to 4. 2 to the power of 3 is equal to 8. So what's happening here? Well, it's just doubling. Right, so 2 to the power of 4 is 16, 2 to the power of 5 is 32, and 2 to the power of 6 is 64. So he has 64 layers when he folds a piece of paper 6 times. So list the elements of the domain and range. So remember, domain is your inputs. So my inputs are 1, 2, 3, 4, 5, 6. And my range is my set of actual outputs. That's going to be 2, 4, 8, 16, 32, 64. Easy peasy, lemon squeezy. So work out the least number of folds that would be needed to have more than 500 layers, right? So this is just going to be some guesstimation. Like we could use logs. But no one wants to use logs because if you're an order level, you know what a log is. If you're a genius at watching this, you know what logs are. And if you're even higher level, you don't want to use logs. So whatever, we're not using logs. We're going to guesstimate it, right? So 7 folds, we have 2 to the power of 7, which would be equal to, oh god, I really should have brushed up on my 2048 game. It is, so 64 times 2, 128. That's after 7 folds. The 8 folds would be 2 to the power of 9. that's going to be 256. Then after 9 folds, it is going to be 512. So work out the least number of folds that would be needed to have more than 500 layers. Well, it will be 9 folds. Right, so 9 folds will give me 512 layers. Now, I'm pretty sure you can't fold a piece of paper more than like 8 times. Isn't that? I don't know. Anyway, doesn't matter. Okay, work out the number of layers after 12 folds. So after 12 folds, well, that's going to be 2 to the power of 12. And it's asked me to leave it in scientific notation. A to the power of 10 to the power of n. Usually your calculator will do this for you, but we'll have a look now. So 2 to the power of 12 is equal to 4096. So scientific notation, I have to bring this decimal point over to my first digit. So 1, 2, 3. So that's going to be 4.096. So to move this back to where it is, I have to multiply by 10 1, 2, 3 times to be 10 to the power of 3. It says here A is an element of natural numbers, so this is going to be 4 times 10 to the power of 3. So it's just a guesstimation, and it's roughly 4,000. Explain what this statement means in terms of folds and layers. So h of 14 is greater than 10,000. Well, this is my input, and my input is the number of folds. So it just means after 14 folds, we'll have more than 10,000 layers. Put a tick in the correct box to show what kind of pattern is made by the number of layers. Well, it's going to be an exponential pattern, right? We'll get more into this in pattern sequences, but it's going to be an exponential pattern because it's going up in twos. So because to get to the next term, we multiply by 2. There you go, bada boom, bada bing. After a certain number of folds, there are k layers. After how many layers will there be 3 more folds? So after a certain number of folds, there are k layers. So certain number of folds, we don't know what the number of folds are, so we're going to call that x. And there are going to be k layers. How many layers would there be after 3 more folds? Give your answer in terms of k. Well, 3 more folds, well, that's going to be 2 to the power of x plus 3. Right? So I've added 3 more layers. But what's that equal to? Well, that's the same as 2 to the x times 2 to the 3, isn't it? So we're using one of my index laws. So a to the x times a to the y is equal to a times x plus y. So I'm using it in reverse. Now, splitting it up, that's going to be equal to 8 times 2 to the x. And 2 to the x is equal to k. So the answer is 8k. So 8k is the number of folds. Finally, after a certain number of folds, there are 2 to the power of p layers. How many layers will there be after 3 more folds? Give your answer in the form 2 to the m, where m is in terms of p. So after a certain number of folds, there are 2p layers. I think it's the exact same process as the last one, and I think I made the last one actually a bit more complicated. I think you just need to multiply by 2 3 times. So k times 2 is 2k, times 2 is 4k, times 2 is 8k. So that's actually another way of doing it. So k, then we multiply by 2, multiply by 2, multiply by 2, which is equal to 8k. That's probably what they were looking for in that one. I was wondering, I was like, that's a bit hard there for Jesus. Right. After a certain number of folds, there are 2 to the power of p layers. Okay, so after a certain number of folds, there are 2 to the power of p layers. How many layers will there be after 3 more folds? Well, That's going to be the same as, well, 2 to the x times 2 times 2 times 2 equals 2 to the p times 2 times 2 times 2. Well, which is equal to 2 to the x times 2 to the 3, which is equal to 2 to the p times 2 to the 3, which is equal to 2 to the x plus 3, which is equal to 2 to the p plus 3. Give your answer in the form 2 to the power of m, where m is in terms of p. Well, that answer is going to be 2 to the power of p plus 3. That's it. That's how many layers we have. How fun is that? Right, let's look at this one now. So this is a 2014 GSA paper. So Paul and Marie have been studying the growth of a particular bacterium in school and to come up with a function to predict the number of bacteria in a colony in thousands after t days. They both assume there are 1,000 bacteria in the colony at the beginning, so when t is equal to 0. Paul comes up with the function 2 to the power of t. Marie comes up with the function t squared plus 2t plus 1. On the grid, plot both of these in the domain 0 to 5. Oh god, they hate me, don't they? Right. To the calculator. Right. So, menu 3. I'll plot the quadratic first. So t squared, I'm not going to be using t, I'm going to be using x. Right? X squared plus 2 to the power of x plus 1. We're starting at 0 in the 5. Go up in ones. Here's my points here. So I start off with 0, 1. So 2, 4, 6, 8. So it's going over 2. So 0, 1 is there. 1, 4 is here. 2, 9 is here. 3, 16 is here. And then the last one, or not the second last one, 4 to the power of 25, which is here. And 5 to the power of 36, which is here, I think. I'm blind as a bat. Yeah, there's it. Right. There you go. There is Marie's prediction. Sorry, that was rubbish. Right, so let's plot now 2 to the power of t. So let's go back now and change my function. So, ding, 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 ding. 2 to the power of x. Starting at 0, ending at 5, going up at once. So my first one is 0, 1. Yeah, gorge, there it is. 1, 2, okay, there it is. 2, 4, right, okay, there it is. 3, 8, right, okay, there it is. 4, 16, there it is. And 5, 32, there it is. There. Right, but do we notice how this one here is getting big quite fast? Right, it's getting big. It's getting bigger quite fast. It might catch up now with Marie's. So the black one's Marie's. I'm just gonna call that M, and this one's Paul's. I'm gonna call it P. There we go. Plot my two functions. Bada boom, bada bing. Right. For parts 2, 3, and 4, you must show your workings and the diagram. Fair enough. Use your graph. Find the difference in the number of bacteria predicted by Paul and the number of bacteria predicted by Marie after 2.5 days. So let's look after 2.5 days. So go to 2.5 here. Go up. Read. So Paul predicts 5. Paul predicts like 5,000, I think. Yeah, I'll say 5. And then Marie predicts what would that be? 10, 12, 13. So Marie predicts 13,000. Remember, we're working with thousands here. And then Paul predicts 5,000. So the difference, 13 minus 5 is equal to 8. So it would be 8,000 is the difference between them. Use your graph to estimate the range of values of t for which both Paul and Marie predict that there will be at least 20,000 people, 20,000 bacteria in the colony. So 20,000. So when did they both predict at least 20,000 bacteria will be in the colony? So we're going to go to 20. That's 18, 20. Here it is. Got to go across. So it intersects with Marie's at 3.5 days, and it intersects with Paul's after 4.25 days. But what's asked me here, use graph to estimate the range of values for t for which both of them predict at least, so both of them will have more than 20,000 in their colony. So we have to pick a point where both of them will have more than 20,000 on the graph, and that would be 4.25, because if you look here, okay, Marie reached it earlier. She reached 20,000 earlier, so we kind of have to wait for Paul. So we have to wait for Paul to get to 4.25 days, and then we can confidently say both colonies have 20,000 bacteria in them. So the answer is t is greater than 4.25. Right, by extending your graphs, estimate the value of t other than t is equal to 0, for which the number of bacteria predicted by Paul and the number of bacteria predicted by Marie will be the same. So we want to extend our graphs now, and we want to see when we predict both of our graphs will intersect. So if we extend them a little bit here, so I'm going to extend Marie's, and then I'm going to extend Paul's, so Paul's gets quicker like this. It will roughly be at this point here, and if we go down and read it, let me change the pencil colour to some colour like green. It's going to be 5.25. So when t is equal to 5.25, they both have the same amount. So the answer is going to be t is equal to 5.25 days. Right, the actual bacteria after 2 weeks of 14 days is 1.6 times 10 to the 7. Based on this, which formula would you say gives a better prediction of the bacteria? Explain your answer. Well, oh sorry, did you see any of that me extending that graph there? Ah, you barely saw it, okay. Sorry, when I extended the graph, I saw that they both intersect at this point. My apologies. Right, down here, by extending, based on which formula do you think is a better prediction? So after 14 days, the actual number of bacteria in the colony is actually 1.6 times 10 to the 7. So we actually want to find out now who's actually more accurate. So just test them. Test when t is equal to 14. So Paul, after 14 days, so his thing is 2 to the power of 14. That is going to give me a mammoth of a number. Wait a minute. So 2 to the power of 14. That's going to be equal to 16384. And then Marie's. So Marie's is going to be, what was it? T squared. So 14 squared plus 2 times 14 plus 1. Put that in the calculator. You're going to get 225. So that is, remember, this is in thousands. So it's actually, that's 16,000 thousands. So add the 2 3s. And then 225,000. So who's more accurate? Well, 1.6 times 10 to the 7 is going to be equal to 1, 6, 1, 2, 3, 4, 5, 6. So which one's more accurate? Paul. Paul is more accurate, right? So the answer is Paul. Paul has the most accurate one. Right. The final. Let's look at the last question here. So this is a 2016 Leaving Cert Ordin level paper. So a company A uses the following formula to charge a customer for a job. So company A uses the formula 30 plus 9.5 H, where AH is the cost of the job in euros and H is the length of time that the job takes in hours. Company B uses the following formula to charge a customer for the same job. So that's company A, that's company B. Complete the table below to show that company A charges and what company B charges for a job that takes up 5 hours. Where necessary, give charge correct to the nearest cent. So a table of values, easy peasy, lemon squeezy. So we're gonna open up our handy dandy calculator. So let's do the first one first. So 30 plus 9.5 H. We don't have H's, so we're going to do an X. So I'm starting at 0, and I'm going up to 5, and I'm going up in ones. So after 0 hours, after 0 hours, I'm charged €30. So that's my calling fee, call out fee, or my standing fee, or my standing charge, etc. After 1 hour, I'm charged $39.50. After 2 hours, I'm charged $49. After 3 hours, I'm charged $58.5. 4 hours, I'm charged $68. And after 5 hours, I'm charged $77.5. Right. Now, Company B. Company B is equal to 10. So you couldn't see that. Ooh. So you couldn't see that there. Yeah, so 77.5. It's a bit smaller. Gorge. Right. So now type in company B. So we have 10 times. Right. So you put your bracket here. 1.74. To the power of H. Again, we don't have H's, so we're going to do it. X. Starting at 0. Ending at 5. Going up in ones. So company A charges you €10 for 0 hours work. After 1 hour, they charge $17.40. After 2 hours, they charge €30.28. Sorry, I'll make this a little bit bigger. So €30.28. So I'm just here. After 3 hours, they charge 52.68. 4 hours, they charge 91.68, or 66 cents, I should say. And then after 5 hours, they charge €159.49. So €159.49. Gorge. Right. On the grid below, draw separate graphs to show the company charges for company A and company B. So let's plot this out. I'm going to do company A in green. So 0 hours, they charge €30. For 1 hour, they charge $39.50. Again, so just make a little dot there. I think that's enough. Like that. 2 hours, they charge $49. So that's going to be like up here, I think. After 3 hours, they charge 58.5. So that'll be just around here. They charge 68 after 4 hours. And then just below 70. And then after 5 hours, they charge 77.5, which is around here. Connect them up. Whoop. There you go. H of X. Or A of X, sorry. Company A. Right, let's do company B. I'm going to do company B in like purple or something, I don't know. Because I feel like it. Right. 0 hours, they charge 10. 1 hour, they charge 17.4. Here. After 2 hours, they charge 30.28. 30.28, so that's just roughly going to be there. Like 3 hours, they charge 52. And so that'll be around 4 hours, they charge 91. After 5 hours, they charge 159.49. So like literally all the way up there. Hi, there you go, and that is company B. So, which company would charge least for a job that takes 2.5 hours to complete? They love saying 2.5, don't they? They always put 2.5 in. So go 2.5, go up, ding, ding. So if you see here, company B charges like €40, and company A charges like 50. So who's cheaper? Company B. So B is cheaper as they charge 40 while A charges around 50. Use your graph to estimate the value of H for which the charge is the same for both companies. So where the charge is the same as the intersect, that'll be this point right here. So when is the charge the same? It will be around here, which is 3.25, because it's a quarter of the way between 3 and 4. So H is equal to 3.25 hours. Find the difference of a job in a cost for a job that takes 6 hours to complete. Now, I don't have 6 hours on my graph here, so I'm going to have to use this algebraically. So, company A, after 6 hours, they charge us 30 plus 9.5 times 6, which is going to be equal to, that's their function, isn't it? Yeah, 30 plus 9.5h. €87. So after 6 hours, company A charges €87. After 6 hours, company B charges something astronomical, I can tell you that much. Right, so their function is 10 times 1.74 to the power of 8 and to the power of 6. So I'm just putting this in my calculator here. And the answer is €277.52. Wow. So the difference, so 277. So it's going to be 277.52 minus €87, which is going to be equal to a difference of €190.52. And that's it. That's exponential equations. That's a load of exam questions I've done there, and they don't really get much crazier or harder than that. Right, I hope this video was some help to you guys, and I'll catch you guys later. Bye.